Hello, welcome everyone. Thank you so much for joining our session. So we're here, me and Chris are here to talk to you today about GenAI pipelines, how to implement a RAG implementation in Microsoft Fabric. And if you don't know what RAG means, then you're in the right place. So before we get started, I will introduce Chris. Are you able to do your little intro?
Yeah, of course. Hi, I'm Chris. I've been with Advanced Analytics for probably about 3 to 4 months now. Coming out of the legal industry for the last 2 years, where I did my master's. Currently working on a foundational model ops platform for an insurance company. That's pretty much me for the last couple of years.
Nice, thanks, Chris. I'm also from Advancing Analytics, been there a little bit longer, coming up to 5 years now. Also work sort of more recently in the FMOps GenAI space. So that's around taking generative AI models and getting them into production. But previous have quite a bit of experience in MLOps, so the machine learning version of that, taking ML models and putting them into production. So in terms of agenda and what we'd like to cover today, we've got 3 distinct parts. I'd like to take you through GenAI, do a little intro into GenAI, set the scene, talk about why generative AI projects are failing. If you listen to the Microsoft Databricks Data and AI Summit, Ali Ghodsi came up with a quote of 85% of GenAI projects never make it to production. So cover a little bit about the reasons why, and then talk about RAG and how RAG is the solution to this. I'll then throw you to Chris, and Chris will talk to you and introduce you to vector databases, why they're pivotal in RAG, and what AI search is. And then we have a fun demo at the end, actually showing you how you would implement this within Fabric. So, GenAI. Everyone is probably sick to death of hearing GenAI at the moment. But just to set the scene on what GenAI actually is, GenAI is a subset of artificial intelligence. It's a specific subset of artificial intelligence. It's actually a deep learning solution which sits under machine learning. So essentially a neural network, typically you'll find they're based on transformer architecture, really around generating new content. And then if we dig a little bit deeper into that, there are some different layers within generative AI. So it's just worth defining this terminology. So within generative AI, so within those models that generate new content, you have a concept called a foundational model. And a foundational model is a model that's been pre-trained, created on an absolute ton of data. I was going to say a swear word there, sorry. on a load of data, and have created these models for other people to use through APIs. If we go a step lower than that, we have large language models, which is probably the one that everyone's most familiar with. So a large language model is a foundational model, which is just text in, text out. So you'll probably be really familiar with GPT 3.5, GPT 4. And then if we go a step below that, ChatGPT is probably the one that everyone's most familiar with. ChatGPT is actually an application built on top of a large language model, which is now GPT 4.0, 4.0. That allows you to interact with it in a chat format. So that's kind of the different levels of terminology there. In terms of what generative AI is used for, why it's gotten so popular, it's got a huge heap load of use cases, and just to throw a load of quick ones at you. Text generation is the classic, creating new content, prompting it, asking it to rewrite something for you, asking it to create new content for you. Question answering, so can you tell me sort of when so-and-so was born? What's the definition for this word? Different question answering things. They can be more domain specific as well. Summarization is one that's slowly starting to be baked into people's applications. So summarizing documents, summarizing meetings. Translation is a big one, translating from one language to another. sentiment analysis, which is like almost like a classification problem, but using large language models. So take this complaints email I have, summarize what the sentiment, how this person is feeling. And then the final one is personalization. You know all of these things about your customer. How can you personalize this product or this piece of marketing for them? So with all that in mind and the huge heap of use cases, why is it then that I've said that 85% never make it into production? So GenAI, great for POCs. When you actually come to implement them, there's quite a few things that you need to be considering. So bias and fairness, like most ML models, it's been trained on historical data. And if that historical data has bias and unfairness baked into it, then that's going to be reflected in your content. So that's always something you want to concern yourself with. Privacy, if you're using ChatGPT, don't tell it anything you don't want it to know. So ChatGPT, if you use the open source one, use the one for free. Whatever you type into it gets saved by OpenAI and rebaked back into the system. And you can get around this by using sort of the Azure flavor of OpenAI, where they say that they're not going to do that, all your data is your own. But that's one thing that you need to be considering when building these applications. And then the classic sort of manipulation, how are people going to be using this? How do you make sure that what you're putting out into the world is going to be safe and usable for people? But the main one you've probably heard of might be hallucinations. So GenAI models are quite renowned for their hallucinations. So if you ask any LLM a question it doesn't know the answer to, it does a really good job of making up an answer very convincingly. And I've pulled out a couple of screenshots here around so this is the Google AI. So if you ask it a question it's not been trained, data it's been trained on before, you can see sort of cheese not sticking to pizza. It's recommending that you use an 1/8 cup of non-toxic glue. Please don't do that. How many rocks shall I eat? It says you eat 1 rock a day because it's not been told you shouldn't be eating rocks. And then this last one here, so train 8 days a week. Can you train 8 days a week? And it says, yes, it will agree with you and it will make up a load of convincing stuff to go with that as well. So hallucinations are a big concern. And if I go a step further than that, so the Retool State of AI report came out last month. And these different stats that you see on the screen here, these are all, these are the obstacles to getting generative AI into production. And you can see that the main one I've pulled out in red, so 38.9% have said they're unable to get their models in production, specifically because they're worried about accuracy and they're worried about hallucinations. So this is a big hurdle that we need to get over. So before I give you a solution, it's worth talking about why do hallucinations happen. So a few different reasons. One might be the training data is inaccurate. So maybe it's trained all of its data on Reddit, for example. Reddit is not the best source, I think, to be training on for accurate data. So maybe it's picked up on satire and it doesn't quite understand the difference, or it's piecing a few things together that it shouldn't be. Another really big one is missing training data. So if you're asking GPT really specific questions, like legal questions or medical questions, and it's not seen that before, then it's going to make it up. It's going to fill in the gaps. And then 2 other ones might be that you've been too vague with your prompting, or that you've specifically asked it to make stuff up and it's hallucinating sort of on command. Now, if we look at the first two reasons, so inaccurate training data and missing training data. So this is the one that we want to resolve the most. So we don't want it to make up answers when the data is missing, or we don't want it to rely on inaccurate data. So what we're going to be looking at in this talk is using the RAG implementation, using RAG to overcome this. So as a bit of an overview of RAG, I can talk you through what RAG actually means. I can talk you through the different levels of GenAI implementations. So if we start number 1, prompting, this is just you ask ChatGPT a question and you get a response. And there are a couple of things that you can do to increase the accuracy of your response. It might be you use different prompting templates. You might do what we call one-shot prompting, which is sort of 1 + 1 = 2. Now tell me what 2 + 1 equals. So you give it an example of an answer and how you want it to look. But that can only get you so far. So it's great if you've got non-specific domain questions, or it's great if you've got limited resources. We go one step up here, which is when we want to look at RAG. RAG is brilliant if you've got large volumes of text data, great if you've got industry specific text data, and if you want to capture the semantic meanings of around your documents. It's not perfect, and we can go through that a little bit more why, but generally it's slightly more complex than prompting, requires you to have a vector DB, and sometimes it's still not accurate enough. So the step up from that would be fine-tuning. So fine-tuning would be you would further train that foundational model. So you would take GPT-4 and you would give it more data. The issue with this is that you need loads of data. You need millions and millions of rows of data. It's very expensive and could be quite complex to do as well. So fine-tuning is we would recommend as a last resort if RAG isn't what you're doing what you want. And then just to kind of reiterate this point, sort of the more complex you go along this line, the more it's going to cost you as well. So prompting, cheap, easy. RAG, slightly more complex, slightly more costly. Fine-tuning, very costly, very complex. And then the next step up, which I didn't describe, was pre-training, and that is if you're making your LLM from scratch. So imagine the 40 million that it took to make GPT 3.5, that would be a pre-trained solution. Thanks, Chris. So RAG, what does RAG actually mean? So R is retrieval. So retrieval is when you would, so when we're coming to do our prompting, before we send our prompt off to our large language model, we want to retrieve some extra contextual data. The A is augmentation, so we would use that extra contextual data to augment that prompt. And then G is generation, so retrieval-augmented generation. So it's take extra data, augment our prompt with it, and then generate our answer. How that would look in practice. So this is what traditional prompting would be. You'd write your prompt, you'd send it to your LLM, you'd get your response. When it comes to RAG, you have an extra couple of steps. So we have our prompt, we take that prompt and we look up that prompt in a document store. Within those document store, we return relevant documents that we think is going to help that prompt, help the LLM answer that prompt. Send both the prompt and the retrieved documents off to the large language model and get a response, which we expect is going to be more accurate and more enriched. So this main solution here really pivots on the document store. That document store, that vector database, that is the main resource, the main thing that's driving a RAG implementation. So I'm going to throw you to Chris, and Chris is going to talk you through what a vector DB is.
Yeah, of course. Thanks, Tori. So let's dive right into vector DBs. And I'm going to try and give you a ground up perspective because it's, yeah, till about 2 years ago, I didn't know what was going on with vector DBs, and yeah, it's all new. So vector DBs are great. They store their data in, they store their data in arrays usually. So vectors are arrays of numbers, and I'll dive into that a little bit. But they're powerful at identifying data points close together, and it's a lot easier to traverse over arrays of vectors rather than traversing over strings of text. And why do we use them in RAG implementations? So they're efficient for text storage. As I say, they're traversing over a string of letters and a whole heap of mess is a lot more difficult than traversing over a vector array. You can also start to perform a lot more nuanced algorithms and approaches to vectors than you can on strings. So I'm going to talk later about semantic similarity a little bit. It's much easier to do that in a vector DB than it is on a string. Then you can start performing, factual accuracy and all of the nice buzzwords you've heard from RAG and generative AI as a whole. But how do they actually work? So we take a string. The first step is tokenization. We take a string, we break that string down into its words, and then we take that broken down array of words and we then give them a vector mapping. We take that vector mapping in an array and we index it into the multi-dimensional space that is a vector DB. When we store that, we can then reference against that vector DB and use what the first letter in RAG is, retrieval, to pick out those specific words that have those vector representations. Now, how do we leverage this within the LLM architectures that we're currently implementing? We vectorize the search query. So say if I have a corpus of data that I've tokenized, I've vectorized, I've indexed, and now I want to retrieve against that. I can then vectorize my search query. So let's say if it was legal, it would be tell me about clause 2A. I would vectorize that search query, send it off to my vector DB, retrieve my response, and then I would take that context that I retrieved from the vector DB and I would send the context and my prompt off to a large language model to form my final response. I would also then rank my responses. Sorry, a step before that, when I'm retrieving from the vector DB, I'd also re-rank the responses to make sure that I was getting the most accurate or similar responses that I needed, or the best context is probably the best way to think about it. Now we have many different popular vector DBs, AI Search, Pinecone. I'm sure you've come across probably AI Search and ChromaDB if you've been reading around this area for quite some time. ChromaDB is quite often the use case for early initial proof of concepts. What I haven't really spoken about much in my slides is popular language libraries that we use to access these databases. So you've got the likes of LangChain, Llama Index, OpenAI's API. You can do quite a bit with all of them, but most common use case we've come across is using LangChain. Llama Index is more advanced and it does quite a bit, whereas LangChain is pretty easy to get on board with and get going with. So specifically, we're going to talk about AI Search, which used to be cognitive search. It's fully managed infrastructure, great for scaling. You can change your SKU that you're using on the fly, integrate seamlessly with other services. And what we're specifically interested in is using that hybrid search. So where we're looking for both the strings and the vectors, and then doing a semantic similarity when we're returning our results. Now, the crux of the matter and why we're here today is that there was a release in Build 2024 where you can now use OneLake as your ingestion source into AI Search. So you can take your documents that are stored in your files or OneLake and you can then crack them, which is taking out those strings of text and breaking them up into those chunks. And then you can index them within AI Search and you can then retrieve against those indexed documents. So that's kind of the first 2 points on this slide, but the third point is that you can do this by the REST API and you can do it via the Python SDK. It is in public preview. That is a major caveat. So maybe consider that if you're thinking about implementing it. But we'll dive straight into the fun part, which is the demo, and hopefully the demo gods are in my favor and everything goes smoothly. So here we have a resource. We have our instance of AI Search and we have our instance of Fabric. I've also set up a key vault to store my secrets that I'm going to use later in a notebook. And I have a managed identity to communicate between Fabric and AI Search. There are several caveats here, but the SKU for the Fabric capacity has to be F64. Anything below that, you can't manage. You can't have managed identities handling your access, and you also need the AI Search service to be above the free tier, so basic, standard, or above. Once you start going into standards, there are permutations of 3 for every different level, depending on your use case. But this, just to give you a quick overview, it's in the UK South and it's a F64. Anything below that, it won't allow you to use managed identities. Now, this is the fabric capacity. So you can see that we have a workspace called Data Science Playground, and we have a lakehouse, and we have some text documents that I've pulled out of Wikipedia. And they're just sat there in our files waiting to be indexed. And this is where we get to what was released in Build 2024, which is the import and vectorize. So we'll run through the wizard together just to give you a good overview of how it all works and what it does. So I'm going to need to go back to my fabric capacity, grab the URL, jump back here, and we're just going to copy and paste that in because it automatically defaults back to the root of the lakehouse. I'm not going to set anything with the lakehouse folder or shortcut because I want everything that's in that root files directory rather than any other folder. So if I had a directory of files, Wikipedia articles, I would put / Wikipedia here if I needed to. The system assigned identity hasn't worked and it won't work. The Microsoft demo tells you to go through and set up that managed identity, which is why you need the F64. So we're going to assign the fabric managed identity that we set up earlier that has access to that fabric capacity and AI search. And another caveat to this is that you need to have Azure OpenAI set up and ready to go, and you need to have a text embedding model all ready to go. At this point, you could use any of these. I'm just going to use my API key and keep it nice and simple. Now, this is the point where you have a little bit more options around how you're vectorizing your documents. So say if I had PDF documents that had a bunch of images in, I could then vectorize those documents, extract the images and convert the context of those images into text and store those results as well. Luckily for us, they're just text files. There's nothing too amazing going on in those files. We're just got some nice clean files. We're going to carry on to the semantic ranker, which is what I spoke about earlier, where we would want to return the most semantically contextual information to our query. So we're going to, and we can also set our indexing options at this point. So say if you're doing batched ingestions and you wanted to keep this updated as possible, you can go for a range or you can set your custom. But we're only going to do it once because we only want to show you how it works. So that's all good. We're going to change our objects prefix to fab demo. And let's go away and create this, which takes probably around 10 to 15 seconds, all going well. But this is where the demo gods come in and there we go. So that's all done. What that has gone away and done is created a indexer, which is looking at that file location, and you can see that it's in progress. But because we have 4 documents, it took about 8.7 seconds, which is pretty good. What that has gone and done is created an index called fab top demo, which is where we have pretty much everything that we need to carry on. So it's created a bunch of fields that we can search against. It's created the text vector, the chunk. So when we're chunking up that document, it's given it an ID, it's given it the content of the chunk, it's given the title, which is the name of the document that it's come from, and the metadata storage path, which is where it's actually located within Fabric. So now we've got that, keep that in mind because we're going to need it for later as well. So on this side of things, we have a notebook. And as I mentioned, there are a couple different methods of doing this, a couple different packages that you can use, but we're going to focus on LangChain because it's probably the most simple to use and the most simple to understand as a first glance of RAG implementations. So LangChain is core. Then we're going to use LangChain community, which is where we store AI search, retriever, and AI search as a whole. We also need to use LangChain OpenAI because that is where we can use the embeddings model. And we're also going to call in Azure Search Documents specifically because we have a custom index. So going back to the AI search, this is those set up through the wizards, different to the default that LangChain uses. So we want to be able to correctly access our indexes using the right field names, the right string types, and all of that fun jazz. So we're just going to call those in. This is where Spark spins up and takes more than 10 seconds. 4 seconds. Okay, looks like this notebook's timed out. Let's quickly just reinstall our packages, which is probably going to take, I reckon, about 25 seconds. While that runs, we'll quickly run through the code. So we're calling in our packages here. We're also calling in the secrets from the key vault that I mentioned earlier. Then we're defining our custom AI search index. So, I referenced chunk ID and chunk and text vector. They're all what relates back to that index that we set up through the wizard. And we pass that into a parameter called fields. We take fields, and this is where we're using LangChain to set up the retrieval and the embeddings from OpenAI and AI search. So you can see that we're setting up our embeddings model over here, and we're using our deployment, our endpoint, and our key. And we're using in the vector store, we're referencing our AI search endpoint, the key, and the specific index that we're using. And this is the point where we're setting that custom index where we're passing fields to fields. Here we're setting the retriever, so using AI search endpoint. This is the content key, which is chunk ID, which is and this is the index key. So later on, we're going to performing that hybrid search. But before we do that, let's just make sure everything's installed. Cool. So all of our packages are installed. Let's call them in to use them. So that's our packages. That's our key set. Here we're just defining how we're going to access that index. Here we're setting LangChain to use our specific endpoints and our specific index schema. And this is where we can go and perform those hybrid search. So hybrid search is a mix of semantic similarity and straight search. And semantic similarity and vector search, I believe. And it will give us the best context on our results. So our question is, what can you tell me about Frodo Baggins and the Shire? This is relating to Lord of the Rings, which is one of the documents that we passed in here. So the Lord of the Rings text, this is the Wikipedia article. Let's just go ahead and run that. So the title is referring to the human readable text format, the human readable document name that we've taken out of OneLake. Content refers to the actual answer. So you can tell that it's not fantastic because it's a straight Wikipedia article. So we have a bunch of spaces in here and the context might not be right because it's just a Wikipedia article. Let's say if you had a more specific use case of legal or a contract, you would have a much cleaner document and a lot more contextual information for your question, and you would be asking very contextual or specific questions in your request. But for our use case of just showing you that we can take a document that's held within OneLake, we can index it, and then we can retrieve against that document. Both we can, while doing that, we can also show you exactly where it's come and the semantic score, search score that it's returning. It goes to show that we can, going back to Tori's 4 points around the issues of using LLMs as a whole, we can solve, and I'm going to question myself because they are. We'll come back to that in a minute. That's kind of the demo. Everything went well. hopefully. Let's jump back into the slides and crack on, because there are a couple follow-up points and a couple things for you to think about as a whole when you're doing this. Just before we carry on, let's remind ourselves of those two issues, which are that we've solved using RAG implementations, which is the inaccurate training data, which is solved by specifically using a document that we ourselves have indexed and searched against, and the missing training data. So this is where you would have specific use case documents that you've indexed and retrieved against. We are able to show you that we're able to do that with OneLake and AI search. So the gotchas, F64 license required. That is that's a big one. That's a big cost and a big upfront commitment to being able to do this. The whole reason behind why you need to do that is using the managed identities. AI search won't be able to talk to your Fabric capacity if you don't have that managed identity set up. The standard license within AI search, it's not a massive blocker, but it's a cost you need to consider. As I showed with the Wikipedia articles, it's not great if you don't have clean documents. You need well-structured documents that you can then index and retrieve against. And the other big caveat to this is it's all in public preview. This, though it works well, is probably going to change over the next year until it becomes GA. So if you're going to go ahead and do this, be aware that there might be some changes to the API definitions and how the SDK works. But I'll wrap up. I think over this talk, we've been able to give you a good overview of what GenAI is, what hallucinations are, and what is RAG, and how it solves that problem of hallucination and the other problems that it solved, and how we can have that pipeline solved by using OneLake, Fabric capacity, and AI search. And we can generate accurate results. Tori, have you got anything to add on before we wrap up?
No, I think that's all good, I guess. Yeah, any questions?